All right, so we're going to round out this unit by looking at some types of chemical reactions. And before I do that, I need to lay a little bit of foundation for some terms and concepts that are going to pop up every now and then, and as well as kind of go a little bit in depth into some things that I mentioned earlier. The first of these side topics I want to look at is the concept of something that is an electrolyte versus a non-electrolyte. The main difference between these things is whether or not they conduct electricity. Electrolytes conduct electricity, whereas non-electrolytes don't. Now, the means by which an electrolyte conducts electricity is because these substances have a plus charge, and then there are substances that have a minus charge. And where have we seen those things? Ionic compounds. So an electrolyte solution is just simply a solution of dissolved ionic compounds. Like, for example, if we took potassium chloride, which is an ionic compound, you got a metal and a nonmetal, and put it in water, it would dissociate into cations, potassium cations, and chloride anions. Now, these non-electrolytes, the reason they don't conduct electricity is that they don't have any charges. Now, there might have some partial charges due to polarity or something like that, but they don't have a full plus. They don't have any ions, I should so to speak, because when they dissolve as a molecular compound or covalent compound, and they don't dissolve into ions. So, for example, ethanol is a covalent compound. When we put ethanol in water, it does not dissolve into carbon ions and hydrogen ions and oxygen ions. It just associates with water, hydrogen bonds with it, and it kind of, I guess you can kind of look at it, just becomes smaller versions of itself. But it does not break up into ions. And because of that, it will not conduct electricity. So you can kind of see here the difference between an electrolyte solution and a non-electrolyte solution, where there's ions present in a electrolyte solution, which, by the way, as a side note, you don't need to know this for anything, but this is why you don't want to swim in a pool during a lightning storm because there's plenty of ions in a pool. And theoretically, and I don't recommend testing this, if it was pure water, completely deionized, there was nothing in it but water, then that water would not conduct electricity. But like I said, I don't recommend trying that. Um, but because ethanol, when it dissolves in water, does not dissolve into ions, it just is individual molecules of itself floating around and the water's surrounded it. These do not conduct electricity. There's no charges to move there's no charges to move electrons around, which is the flow of electricity. Now, that doesn't mean all molecular compounds um, are non-electrolytes. There are some, like for example, let's take HCl. HCl is a non-electrolyte. It's a molecular compound, it's covalent. But if we put HCl in water, it will react with water to produce something with a positive charge. This is called hydronium, and produce something with a negative charge, chloride ions. So we get positive ions, negative ions, and now this solution is electrolytic. It is an electrolyte solution. Even though HCl started off not being an electrolyte, it reacted with water to produce ions. And this is going to kind of lead us to our other little side trail here. because HCl, you might recognize the formula, is hydrochloric acid. So let's talk a little bit about acids and bases. I'm not going to spend much time on this because you're going to go over this a lot more in depth in Chem 102. So I'm going to give you like broad strokes, just some things to know, and then you'll talk a lot about it next semester. So the definition of an acid, and there you'll learn that there's a few, but the main definition that we're going to go off of is that acids are substances that donate a proton or a hydrogen ion. If you think about what a hydrogen atom is, it's just one proton and one electron. If it gives away that electron or that electron leaves for whatever reason, then all you're left with is a proton. An H plus ion, cation, is just simply a proton. Now, because most of the time our acids that we deal with, especially in GChem, are in water, it's important to note that H plus, when it's in water, forms an ion called hydronium. So H plus basically form a bond with water to make hydronium. And you'll see me use these interchangeably. So H plus, H3O plus, you'll use them interchangeably. You'll see that used interchangeably as well when we get into OChem. Now, how do you identify an acid? The easiest way is know your nomenclature. So if you see a formula, you should just be able to recognize that as an acid. A lot of the acids in general chemistry, the H appears at the very beginning of the formula. So that's quite common for a lot of inorganic acids, but not so much when we start talking about organic acids. And that's way, way down the road. Again, that's kind of organic chemistry. But if we take this, for example, this is nitric acid. Hopefully you've already named that. And water. Nitric acid will react with water to form hydronium and nitrate ions. I want you to take a close look at what happened to this hydrogen. That hydrogen is no longer attached to the nitrate. It was donated to water. So nitric acid donated an H plus to water, which makes it an acid. Because now it's over here. Now, on the flip side of this leads us to the other part, is that since water accepted that proton, it's what we call a base. So the definition that I want you to know right now for a base is it's a substance that accepts a proton. An alternate definition, which is going to be very common in GChem, is a substance that forms hydroxide. So OH minus, when it's placed in water. So if we look at, again, let's go back to this reaction of nitric acid with water. Nitric acid donated its proton to water, so that's why nitric acid is the acid. Water accepted that proton to become hydronium. That's why water is the base. Now, some of the most common bases that you're going to see in this class, or I should say in general chemistry, are metal hydroxides. So I'm just using M there as a generic metal. Like, for example, sodium hydroxide, potassium hydroxide, calcium hydroxide, and so on. And you also will see ammonia quite a bit, NH3. as a base. Now, how do these hydroxides act as a base? Well, we take sodium hydroxide, and if we put that in water, it will dissolve to form sodium cations and hydroxide ions. So remember how I said the alternate definition for a lot of inorganic bases is it's a substance that forms hydroxide when placed in water. Now, let's look at ammonia here. How does this act as a base? So when we put ammonia in water, there is a proton transfer where the nitrogen will pick up a hydrogen to form ammonium, and water will donate a hydrogen to make hydroxide. So notice what's happening here is that water is giving up a proton to become hydroxide. Ammonia gained a proton to become the ammonium ion. And the last thing I kind of want to highlight is I want you to look at what water is doing in this reaction and what water is doing in this reaction. Here, water is the acid. In the previous reaction, the one at the top, water is acting as a base. So it's important to note that water can act as an acid or a base. This is a trait called amphiprotic. So we refer to water as amphiprotic because sometimes it can act like an acid and sometimes it can act like a base.